Hey guys, welcome back to Introduction to Computer Networks at NTU. Alright, it's another new week. Let's check out the announcements. How about that? Let's go straight to bullet 3. These are the assignments due this Saturday. Good news, no PA will be due this week. Okay, just 4 quizzes. And the last 3, quiz 9, 10, and 11 are straightforward. The only open-ended one is quiz A, which we will work on today. All right. So this week, I think relatively light. And what we will be doing is mainly to finish chapter 2.1, which is an overview of the application layer protocols. And I think the rest of the week will be focusing on introducing a very important application called the World Wide Web. Okay, so we'll talk about the application. We'll definitely talk about the protocol that supports this application, which is called HTTP. Okay, and there are some additional mechanisms that people implement and design to help speed up web browsing as well. So that is pretty much what will happen this week. Now another bullet, this is kind of looking a little bit more ahead, next week and 2 weeks down the line. So there's no PA due this Saturday, but PA3, the next one, will be due next Saturday. And if you recall, the first week of the semester, PA3 and 4 are going to be challenging. And PA3 being the first program you need to turn in that uses socket. Recall socket? Yeah, last week, something that very important we talk about is that when you are designing a network application or internet application, there are 4 very important design elements. First is the communication model. Is it going to be client-server based or peer-to-peer? Or a hybrid of these. Now the second thing is after you decide that how many devices are going to be connected and which is going to be the server, which is going to be the client, then you need to start communicating these programs. And that function call or that particular feature in programming a network application is called socket. So we talk about socket. When you start a socket, you need to give a number, you need to specify a few things. You need to specify a few parameters, including what is the transport layer protocol you're going to use, and including something new we learned last week, the port number, because the IP address identifies only a network interface. A lot of times it meant a end system, a machine. But if you have multiple processes running on a machine, then you need to set these different processes apart. And so there's another ID called the port number to separate the processes. So PA3 will be your first time to try to implement a network application and the client side. And you need to open the socket to connect to the server. The server is already running on the PA server. Okay, and I see many of you have started working on PA3. Good for you. And you might be able to finish PA3 this week. That is, hey, it can only be better, right? So if you have more time and if you can wait to start the next one, go on and work on PA4. Now for PA4, you're going to need a port number. So Polly is going to update the port number assignment because this semester we have an explosion of number of teams. So if you go to Golan, there's a port assignment link here in the course page. Yeah, so look at the upper right of the screen. The port assignment, if you click in, it's a PDF file that assigns the port number for each team. Okay. And this semester we have 21 teams. Well, 20 teams, but team 3 probably find another course in priority and open up a C. So congrats to team 3. So he left. So there are 20 teams, but let's keep the team numbers the same throughout the semester, okay, for consistency. Team 21, essentially your team number is going to be 12021, but I'll try to update this PDF file. Yeah, hi Brian, hi Ricky, and hi William. So this is, in case you want to start PA4, something that you want to be careful about. Because, guys, think about it. Right? Each of you will be writing your own server for PA4 and you'll be testing it. So you'll be running that PA4.go and it's a server. But PA server, PA workstation is just one machine. There's just one IP address for it. But you guys' program should not be conflicting with each other, accepting packets from another client. Okay, from another team. So you guys will need to run your PA4 on different ports. Yeah, that is what this port assignment is for. Okay, so if you follow through the PA4 description and the walkthrough videos, the idea of your PA should be running on, of course, the PA server's IP address is important. But you guys will be running on different port numbers is even more important so that you guys will not have conflict with each other. If somebody else uses your port number to start PA4, then you won't be able to start your PA4 for testing. So, and it will look like an error message. So just be careful. For PA4, you need to use just the team's port number. And also, if multiple of you in a team try to program PA4 and test PA4 at the same time and using the same port number, okay, that might happen. Then you might also have this issue that, hey, somehow I couldn't start my PA4. Yeah, chances high that your teammates might also be on PA workstation working on it. So coordinate with your teammates so that you won't be programming PA4 and testing them at the same time and creating an error messages that is not because of syntax issues, okay, or semantics issues. It's more just that they conflict. Where can I check the port number? Exactly. So it's from the course page. if you scroll down, click into the Golang link. This is the programming assignment. Yeah, on the upper left, there's this link called port assignment. Yeah, thank you, Sherman and Henderson. Yeah, Ricky joined a little bit late, so he probably missed the part. Okay, so Ricky is here. Port assignment. Click in here, you see the port assignment. So one port for one team. So what I was just talking about is that in case multiple team members are trying to do the coding at the same time, then you might run into this problem that happens in runtime. Not in the programming time, not in the compile time. It's a runtime issue. The port number is there, but you guys might be using the port number at the same time. Okay, so just coordinate with your teammates, then you should be fine. So that was PA3. A little bit further ahead, exam 1 is coming. Guys, this is week 4, right? We have 3 exams in the semester, and exam 1 is coming in only 2 weeks. All right. So next week there's gonna be a preparation session. So you guys can actually set up your webcam and call into the Google Meet session and confirm with Polly whether the camera angle is all right. Yeah, because we need to take take your headshot from shoulder up during the exam. All right, so you need to have your webcam active all the time during the exam. Okay, so it's part of it's a very important part of making sure that during the exam everyone attends, and we get a certain sense whether you guys are working on your own exam in the meantime. All right, so again, just like every Tuesday session, there are quite a bit of things we need to talk about to start the week. And now the topics. Last week, we've already started talking about the 4 elements, the communication model, the socket. Now, one of the parameters you need to define to set for your socket is the transport layer protocol you use. And that has something to do with the quality of service requirement of your application. And that means it depends on the nature of the application. It depends on what the users would really like, or users feel that a good service is. You find out what the QoS requirement is. And last week at the end, we already talked about 4 kinds of quality of service requirements. So there's just one video we need to play that covers QoS, because those 4 requirements sound a little bit abstract, right? Reliability, delay, timing, throughput, and security. That sounds a little bit vague. When you are really designing a network application, how do you know what the users would expect? What property would the users like? Okay, so this video we're going to play next is to go through a few existing applications. And let's discuss what the QoS requirement for these existing applications are. Then from these examples, you might see a little bit better. Okay, if you are asked or hired by a company to design a specific application, what QoS you think the users will demand? All right, so let's check out these applications that are well known and the QoS requirements for these applications. Let's go over a few common applications and see if we could sort out their quality of service requirements, or in short, QoS requirements. First application, file transfer. Transferring files are static objects, most of them text-based. Therefore, in terms of data integrity, we demand 100% reliability. File transfers, we do not expect they arrive in a few seconds. Okay, so it's not delay sensitive. As a result, there's no strict bandwidth requirement. Therefore, the throughput part of the QoS, elastic. You can probably imagine email and web objects. These are transferring also files, email files, transferring web pages, okay, web page files. Therefore, the QoS requirements very similar. The second application here is real-time audio video. So, first of all, the nature of content, audio video, different from text. Therefore, keyword, non-text, it can be delay tolerant. Okay. Another is it's real-time. That means it's interactive. That's another keyword, which means we do have delay requirement. And for real-time, that's showing the audio, video that's happening right now. So the delay needs to be less than hundreds of milliseconds. So you feel like it's happening right now. Audio, video, now there's time sensitivity. Therefore, we need to maintain minimum bandwidth. So there's a bandwidth requirement. And the requirement for audio, lower, video, higher. These days, some users might actually expect even higher bandwidth for video. Now, can you think and push a little bit and see if you know the QoS requirement for stored audio video? Well, first of all, keyword, audio, video, non-text. Therefore, you can probably guess data loss here is loss tolerant. What about the delay requirement for stored audio video? It should still be some requirement, but probably not as strict as the real-time audio video. And you're right. Delay can be a little bit longer. But given that there's delay requirement, the throughput is still hard. We still need to make sure that there's a minimum amount of bandwidth available. And audio video, the bandwidth requirements are because of the nature of the content. So it will be the same. Audio, 5 kilobits per second to a megabits per second. Video, 10 kilobits per second to 5 megabits per second. Now what about this one? Yeah, interactive. The keyword is similar to the real-time nature of this application, isn't it? Except that this is now game data. So you can imagine, delay requirement here, just as strict as real-time audio video. Is it loss tolerant? It's a little bit tricky, isn't it? What about throughput? If there's delay requirement, then there's usually a throughput requirement, but it should not be as high as video or even audio. So here, just a few kilobits per second. Game, this part is debatable. For some games, for example, shooting game, some of the players would argue, I want no packet loss. Okay? But for most of the interactive games, it's okay to have some loss. Okay? And then the users, the players, can try to repeat actions to make it up. What about text messaging? Keyword text, so no loss, obviously. Throughput? Yeah, it depends a little bit on the delay sensitivity, isn't it? And text messaging these days, yeah, it's also debatable whether it's time sensitive. Some will say yes, some will say no. Okay. But you see also that the delay we experience in text messaging, most of them are probably thinking delay, not network delay. Okay. All right, so you get a sense, right? For text-based applications, reliability seems to be a requirement. And for video-based applications, then you can imagine the throughput requirement will be higher, right? Now, timing, then it's a little bit tricky. You see that instant messaging, it's text-based, okay, unlike a World Wide Web or email. So World Wide Web email, people do not expect that the emails will come immediately, right? But instant messaging, because it's instant, then even though it's text, then people kind of expect short delay. Similarly, for video audio, if it's playback video, then people probably do not expect really short delay as long as the video is smooth. But for interactive ones, such as what we're doing now, then shorter delay ensures better interaction. So these are the nature of the application. It depends on the content you're transmitting, but it also depends on the interactive style and the expectation of whether this is going to be instant or not. Okay, so the nature of the application, what the users will expect. Okay, so it's a little bit complex. Okay, exactly what QoS requirements are for a particular application. Now, next, okay, we'll talk about transport layer because, hey, the reason that we're talking about QoS is because when you define the socket, you need to specify which transport layer protocol you use. Okay, so let's introduce transport layer just a little bit, enough to get by configuring sockets. Okay, so first video is to introduce the two transport layers we have, okay, TCP and UDP. In order to find out what is the right transport layer protocol for an application, we also need to know what the options are. We do have two, TCP and UDP. TCP is the one more elaborated. UDP is very primitive. Let's focus on TCP here. The reason it's more elaborated is because it provides reliable transport. Think, a sending process and the receiving process. If we connect the two of them using a TCP at transport layer, data will always come to the receiver 100% correct. There's not going to be error. There's not going to be lost packets. How do we do that? Well, let's talk about that in Chapter 3. In fact, that's the main content in Chapter 3. For now, keep in mind, TCP provides reliable transport, no data loss. Second, TCP also does flow control between sending process and receiving process. The sending process here is checking whether the receiving process is busy or not. In case it's busy, the buffer gets full because data comes to the receiver and gets buffered temporarily here. If the receiving process is a little bit busy, the speed that we extract the data out to the application could be slow, so buffer builds up. If the sending process is sending data too fast, those data arriving to a full queue, full buffer, data get lost. If TCP is doing all it can to try to recover from loss, it doesn't make sense that sending process is sending data too fast to create data loss. So, flow control means some sort of communication going on between the receiving process and the sending process so that the sending process will slow down. Congestion control. It's a little bit similar to flow control, but it's between all these other routers in the middle of the path from the sending process to the receiving process. In case any of the buffers, okay, in the middle on the internet is close to full, sending process slows down. If the buffer is no longer full, packets can go smoothly, speed also comes back up. Okay, so that is called congestion control in TCP. This, in fact, is also one of the main content that we'll talk about in Chapter 3. So for now, just keep in mind, TCP does reliable transport, flow control, congestion control. TCP, however, does not do this. Timing guarantee, minimum throughput guarantee, security guarantee. So the other three QoS requirements we talked about, TCP does not provide. The only QoS guarantee it provides is reliable transport. So this is TCP. Now there's one more feature about TCP. It's called connection oriented. To set up a TCP connection at the transport layer, the sender and receiving process also do some sort of control message exchange to set up a connection. So this part of internet, although it's a packet switching network, but the behavior is a little bit like the circuit switch network. And there's a reason for it. Okay? This is so that we have more communication so we could recover from errors. UDP, it does not do reliable data transfer. There's nothing really going, no more communication between the sending process and the receiving process. Sending process is send, receiving process is receive. It does not provide flow control, congestion control, none of these timing, throughput, security guarantee either. There's no connection set up. So this is really the native packet switching network transport layer service model. Now you know, TCP essentially does nothing. You're right. The question is, why do we bother having UDP? Why don't we just use TCP? Yes, if you recall, among all these applications we've mentioned, text-based content, we prefer reliable transport. But is there other kind of content that reliability is not necessary? It's okay to have some loss. Yes. Sending audio video is not necessary to have 100% reliability. So quite a few of these audio video multimedia services, multimedia applications, prefer using UDP as the transport layer service. Yeah, so there's TCP, ensure reliability, and UDP there sends audio video traffic which does not require reliability. Okay, so you have two different flavors of transport layer protocols to choose when you set up a socket. Okay, Next video is still about transport layer. Just like after we talk about the QoS requirements, we go through a few examples and discuss what the QoS requirements are. Let's go over a few of these network application examples as well. And let me tell you which transport layer protocol each of these applications uses. Okay. Here, let's go over some common applications and see what transport layer protocol they pick. Email, well, in fact, remote terminal access, remote logging, such as the terminal you're using to remote logging SSH to the PA server. Web downloads, file transfer, all these are what? Text-based, static objects. Reliability important, but it's elastic, no delay requirement. So, not surprising, you see them all using TCP. So these are just the specific protocol, okay, each of the application is using. Email is the application. The application layer protocol is called SMTP, Simple Mail Transport Protocol. For World Wide Web, this is the application. The protocol supporting World Wide Web is HTTP. File transfer, the protocol, FTP, standing for File Transfer Protocol. Now, these two other applications, streaming multimedia such as Netflix or YouTube Live, audio, video, reliability is no longer required. Therefore, you see, some streaming multimedia applications use UDP, but some stick to TCP. Internet telephony, Google Meet that we're using also on the side is one such internet telephony application. It's audio, video as well. So UDP. And sometimes some of these internet call services are TCP. And that takes us to quiz 8. Okay, let me go to the whiteboard mode so that I can write on it. So this is quiz 8. Okay, so what I'm showing here are 3 kinds of games. Okay, 1, 2, 3. And guys, pretend that you are hired by a game company. Okay, and you will need to design which socket to use for each of these games. So let me explain each of these games. So this one is called Farmville. It's an ancient game. It's an ancient web-based game. So what you do is to plant seeds and take care of your plant and wait until they harvest, wait until your flowers blossoms. Yeah, just like what the picture shows here. Okay, and part of the gameplay is also that you can visit your friends' garden as well and appreciate their crops. Similarly, they can come over. Okay. You can also drop by your neighbors and then you might find a particular crop interesting and you want to plant them as well yourself. Then you can probably steal some of the crops and see if you can plant it in your garden. Okay, so that's the kind of gameplay. After you plant the seed, you need to wait in real time for a while for the flowers to grow or trees to grow, things like that. Okay, so that's kind of the pace of the game. The second one is PUBG. It used to be very popular. It's a first-person shooting game. And the game is really cruel. Just a bunch of the players will be dropping to a certain area. And to win the game is that you kill each other until there's the last one standing. Okay, so in that area, if you explore, you might find better weapon, better armors, better helmets. And so you try to kill each other. And I suppose in such a game, it's important that if you hit fire, a bullet is really fired. And if a fire command is a message, and you want to make sure that the message gets to the server reliably and hopefully quickly, right? Otherwise, it's not going to be a test of your reflection time. It's not going to be a test of your internet connectivity. All right. So that's the second game. The third one, this one is the most complicated. It's called RO. It's a massive multiplayer online game, and the gameplay is really rich. So what I'm showing in this picture is just you and your friends sitting outside of a town and having a conversation. And the conversation could be like planning for a big raid, tomorrow. A raid is oftentimes a big, gigantic monster, and a team of you with different occupations, different skills work together to combat and hopefully win. And if it's a success, then usually you get uber treasures, like a uber weapon or something like that. Okay, those are usually rare. Okay, so yeah, in these role-playing games, it can be easy just chatting, but it can also be very intensive, right? Battling or training combat skills. All right. So for each of these games, please, okay, tell me whether it's TCP or UDP you will use to transmit the game data. Or, hey, a hybrid of TCP and UDP to transmit data. Okay, so pick one for each kind, but most importantly, tell Polly why. Okay, good. And you can see that this problem is, this quiz is the open-ended one. So let's go to the score space to channel W4 quiz 8. And guys, you have 8 minutes, okay, because there are 3 games. And for some of the games, it might take a little bit longer. And you might want to gather your teammates, have a short discussion as well. Okay, so 8 minutes, let's start counting time. And guys, time up. Yeah. So I saw you guys giving this a thought. Very well done. Yeah, I see that many of the teams seem to go with TCP for slower pace because delay is not an issue. In that case, then you could do TCP and ensure reliability. Okay. For PUBG shooting game, many of you chooses UDP because timing is extremely important. Yeah. And for RO, many of you say that both. For some part of the gameplay, timing is important, use UDP. And for the other parts, that reliability is important, TCP. So chatting might not be so reliability required, but hey, in such a massive multi-user online game, what you do also is shopping. Yeah, you go to a market and you shop for these weapons. And sometimes some of the shops are opened by other players. So it's not exactly trustworthy. So it's probably better to use TCP for that kind of communication in the game. So I guess you guys kind of pick up a certain sense that reliability is not a bad thing. As long as delay is not an issue, then you go with TCP. But if delay is an issue, then it's a little bit more critical, right? You would prefer UDP. But in some cases, so for example, I think there was one team. Yeah, for example, same team 1 here says for PUBG TCP, because what if the fire commands get dropped, right? It's just as bad as bad timing. Okay, and another one. I think further down here. Yeah, I think here. Team 9. PUBG, hybrid TCP UDP. So video data probably UDP is fine. But for shooting, right? TCP is kind of good in showing reliability. So perhaps for PUBG, this type of game, the ideal case is TCP, and make sure that the distance between the client and the server is very short. Now that's another way to reduce delay. Or in a network where you do not see a lot of congestion, meaning there are not many packet losses, then UDP might be okay. So perhaps offering for PUBG this type of game, both UDP and TCP, and dynamically switch the protocol depending on the network condition. How about that, guys? Okay. Yeah, so think. And you see also that as you guys are posting solutions, I'm also grading. So look at the upper right of the screen. You see that I'm assigning score for, can I scroll all the way down, up? Yeah, I'm already scoring for QA. And you'll see that usually the one being assigned a highlight, a bonus, are the ones that give answers that are unusual and try their best to explain. Okay, so you see a lot of times, especially when it's more real in life, there's no correct answer. It's more considering trade-off. And the trade-off might depend on what the current condition is. In one condition, one solution might be bad. In another condition, another solution might be better. So you need to think it through. So Polly was trying to give an example. If Polly is designing it, I'll probably do both and then allow the game client to dynamically decide, depending on the measurement of the delay and packet loss, and adjust which protocol to carry the data. Good. And I'll finish the grading after the lecture. But good to see you guys having some thoughts and then putting your answers there. So in some cases, I like an answer. For example, Team 15. So Team 15 start by telling this. So it's like, I've discovered that there's a certain principle deciding whether I use TCP or UDP. Okay, so so Team 15 is telling what's the logic behind the decision already, and then begin to walk through the games and saying that these two will be UDP because according to the principles I've come up with, they are in the UDP category. And Farmville, delay is not an issue, TCP. Yeah, but you see that Team 15 or all of you, you might have a certain principle after studying TCP, UDP, and a variety of games. But as there are more new type of games showed up, revise your principle. And usually you will come up with a principle that is more well-around and covering more cases. All right, so again, an open-ended problem. You know what? As you are answering these quizzes, you are designing already a network application. In this case, 3 network applications because there are 3 different kinds of games. All right, I hope it's good exercise. And now we move on to the next topic. It's called secure transport. If you recall, there are 4 QoS requirements. One of them is called security. But when we were introducing TCP and UDP, obviously neither of them provide security. Yeah. So in this topic, we're going to talk about a protocol that supports secure transport. But that protocol is not exactly in the transport layer. It's actually implemented in the application layer, but sits right below the application. That protocol was originally called SSL, and this video introduces SSL. And it's 3 minutes and a half. All right, secure TCP. This is the next topic. Yeah, if you recall, when we're talking about these service requirements, right, there are 4 of them. Reliability, which is supported by the TCP. Delay requirement, right, which is somewhat supported by using UDP. Bandwidth requirement, and that might be better supported by UDP, but TCP might do a reasonable job. But the 4th, security. Yeah, the fact is that TCP and UDP, none of them provide security. There's no encryption at all. If we send passwords through the internet straight using TCP or UDP, it's essentially clear text. If there's someone intercepting the message, that someone gets access to our bank accounts or gets into our Amazon.com's account. So none of these cases is good. Big money loss potentially involved. So demand is growing, therefore there is need of these secure layers. So this is secure socket layer. So what it means is that before messages go through the socket and go out on the internet, let's make sure that it's secure. Okay, so it's to provide encryption to messages that's going into a TCP socket. As a result, then we can encrypt messages using a key, or we could verify the receiver using a certificate. Okay. So this is just as important as trying to make sure that the data is confidential. Okay, because how do you know if this server that you are contacting to is indeed a Google server, right? How do you know if it's indeed your bank server? So this is to identify whether the person you're talking to is indeed the person you're expecting. This is just to make sure that no one can understand the message. No third person can understand the message. Okay. And SSL is at application layer. Yeah, it's on top of TCP, therefore it falls in the application layer. But it's also right underneath the application layer protocol, so message go through the application layer protocol, and then to the SSL, and then to TCP. Okay, so this picture below illustrates what I meant here. So SSL right here, right underneath the application layer protocol, but right above the transport layer protocol. Last, SSL socket API. Yeah, to implement SSL, there are APIs available for each programming languages. In Chapter A, you will see Python's API to try to encrypt messages before they send messages out onto TCP socket. Now, in this semester, towards the end, one of the PAs, you will also be exercising the APIs in Golang to do secure TCP. But there, we'll be using this, TLS, Transport Layer Security Support. Yeah, this is actually a newer term for SSL. So nowadays, people don't call the security support over TCP SSL. They are all referred to as the TLS. Okay. If you think about it, this makes a lot of sense because, hey, SSL there is not really a layer. It's more a support for security. All right. All right. So that was SSL/TLS, and you cannot forget about SSL. Okay. From now on, we just refer to this secure transport support as TLS. And that's pretty much all the time we have today. So we're going to talk about exactly how TLS work first thing tomorrow morning. Okay, and that is the part that requires knowledge on the public key cryptography. So guys, you guys still have some time. So later tonight, go over those overview videos about public key. Then tomorrow it'll be easier for you to follow the video explaining how you transmit password over the internet. You obviously cannot send it as a plain text, right? You need to encrypt it. But the thing is that in order to be able to encrypt, you need to communicate with the receiver. There's a password we share, but you cannot send the password in plain text. So you see, very challenging to send password over the internet. And the solution is called the public key crypto. And that actually wins the authors of the public key crypto a Turing Award. That is like the Nobel Prize for the computer scientist. Okay, and the mechanism is very interesting. Okay, it takes advantage of some number theory stuff. Okay, prime numbers to be more precise. All right, good. So that's all for today, and tomorrow let's continue talking about TLS, and that's gonna finish chapter 2.1. And from that point on, chapter 2 will be more about talking about those popular internet applications and the protocols that are designed to support these applications. And there are going to be 3 examples. First is web, so we talk about HTTP next. Second, email, and we'll talk about the protocol to support sending of the emails. And next, DNS. And these will all be client-server based network applications. After that, we're going to talk about a peer-to-peer based network application called BitTorrent. And that's probably all that we'll cover in exam 1. All right, good. With that I say goodbye. I see you tomorrow. Okay, bye. Okay, bye. Let's just hope the weather stays as pleasant as today, the rest of the March. Okay. Okay, bye.